as a continuation of refraction through a thin lens or refraction through a lens, we shall derive today the thin lens formula. So before deriving the thin lens formula, let us study the Sine convention that is applicable to all type of lenses. So the Sine convention is something like this. Remember that all the distances are measured from the optical center of the lens. All distances are measured from the optical center of the lens. Next, distances that will be measured in the direction of the incident ray are considered as positive. Distances measured along the direction of the incident ray are considered positive, whereas distances that are measured opposite to the direction of the incident ray are considered to be negative. So distances measured opposite to the direction of the incident ray are considered to be negative. All the heights above the principal axis, all the heights that are measured above the principal axis are considered to be positive. Heights above principal axis are considered to be positive, whereas all heights below the principal axis are considered to be negative. Heights below principal axis. So this is the Sine convention that is applicable to all types of lenses. It is equally applicable to a convex lens as well as a concave lens. So on the basis of this Sine convention, we shall derive the lens formula, also called as the thin lens formula. Because whatever lens we consider for ray diagrams as well as in numericals, they will be taken to be thin lenses. So let us derive the lens formula. It is slightly different from the mirror formula. The mirror formula that was applicable to spherical mirrors was 1 by V plus 1 by U equal to 1 by F, whereas the formula that is applicable to lenses is 1 by V minus 1 by U equal to 1 by F. So let us derive that particular formula. The thin lens formula is, it is 1 by V minus 1 by U equal to 1 by F, where V means the image distance from the optical center, U is the object distance from the optical center, whereas F is the focal length of the lens. Now remember that by focal length we always mean the second principal focal length. So let us consider a convex lens. This is the principal axis of the lens. Let me consider an object, a ray parallel to the principal axis, will obviously pass through the focus. So suppose this is the focus. It is obviously the second principal focus, and the ray passing through the optical center goes undeviated. You know that a ray passing through the optical center goes undeviated, and suppose they both meet at some point where we get the position of the image. So this is the position of the object. Let me call the object as AB and the image as A dash B dash. F is the second principal focus. The object distance from the optical center of the lens, suppose this optical center is called as O. This distance is U. That is, the distance of the object from the optical center is U. The distance of the image from the optical center is suppose V. And the focal length, or the second principal focal length, is the distance from the optical center to the second principal focus. Remember, I repeat again, by saying just the focus or the focal length, we always refer to the second principal focus or the second principal focal length of the lens. So now this formula can be proved using similarity. So if you note, with respect to triangle ABO and triangle OB dash A dash, then what we see is triangle ABO. This angle is equal to this angle, they are vertically opposite. This is perpendicular, this is perpendicular, so the angles are also equal. So you can say that triangle OAB is similar to triangle OA dash B dash. So from the similarity of the triangle, as we know that the sides are proportional, so with respect to OAB, let me take AB, and with respect to O dash A dash B dash, let me take A dash B dash. That must be equal to OA by OA dash. So this is suppose our equation 1. Similarly, if you consider this triangle, let me call this point as the point P. If you consider this triangle POF and triangle A dash B dash F, this angle is equal to this angle. This is 90 degree, this is also 90 degree. So if you consider triangle OPF, it is obviously similar to triangle A dash B dash F. Triangle A dash B dash F. So we can write OP by A dash B dash is equal to OF by A dash F, because corresponding sides of similar triangles are always proportional. So if you observe the diagram, OP and AB are same. OP is equal to AB. So here I can write now AB by A dash B dash is equal to OF by A dash F. So now this is our equation 2. If you note, equation 1 and equation 2 both are AB by A dash B dash. So you can say that OA by OA dash is equal to OA by AF, A dash F. So from 1 and 2, so I don't want to omit the figure because that will be required for the calculation of the magnification. So this is V. So now from 1 and 2, this is V. So from 1 and 2, what we can write? And 2. From 1 and 2 I can write obviously OA by OA dash is equal to OF by A dash F. Now if you can note it down, I will do the next set of calculations. So from this I will proceed. OA by OA dash is OF by A dash F. So let me omit this portion. So from here on we proceed. OA. What is OA? OA is the object distance. And object distance is measured from the optical center. Now you see that this is the direction of the incident ray, and we are measuring the distance u along the direction opposite to the incident ray. So this OA, which is u, must be taken as negative. I repeat, distances measured opposite to the incident ray are negative. So OA, we are measuring the distance from the optical center. So optical center to object. If you move from optical center towards the position of the object, you are moving opposite to the direction of the incident ray. This is the incident ray direction, we are moving opposite to it. So this will be negative, minus U. OA dash, whereas OA dash, optical center to the position of the image, we are moving along the direction of the incident ray, because this is the incident ray and we are moving in this direction. So this will be plus V is equal to OF. OF is, again you see, that is the focal length, and this distance is along the direction of the incident ray. So this F should be taken as positive again. And A dash F, instead of A dash F, I can write OA dash minus OF. OA dash, instead of A dash F, I am writing OA dash minus OF. So now let me omit this portion. So from this equation, therefore we can write minus U by V equal to, instead of OA dash, what we can write? Instead of OA dash is again the image distance, that is along the direction of the incident ray, so that is B. OF is the focal length which is in the direction of the incident ray, so that is F. So if we cross multiply, that will give you minus UV, minus U into minus F, that is plus UF equal to VF. Now if we divide this entire equation throughout by UVF, so if we divide this entire equation by UVF, what we will get? So from here on, I proceed minus UV by UVF. We are dividing throughout by UVF is equal to VF by UVF. This was the point A. Okay. So then UV and UV will cancel. We will get minus 1 by F. UF and UF will cancel. We will get 1 by V is equal to VF, and VF will cancel. We will get 1 by U. So now if I rearrange, I can write 1 by V minus 1 by U equal to 1 by F. It will go on the other side. It will become positive. So thus we have reached to the formula that we needed to derive, which is called as the thin lens formula or the lens formula, and that is 1 by V minus 1 by U equal to 1 by F. So this is the derivation. Now if you want to know what the magnification is, so if you can note it down, I will then omit it. So now magnification is actually equal to the height of the image by the height of the object. So if I define what is magnification, it is either the ratio of the size of the image to the size of the object, or it is also the ratio of the height of the image to the height of the object. So magnification if I denote it by m, this will be equal to height of image by height of object, and this is usually denoted as hi, that is height of image by height of object. Now we will see that this ratio is actually equal to the ratio of the image distance to the object distance. So therefore this is what I write, n equal to hi by ho. We have to apply sign convention when you are applying the ratio of heights. Heights above the principal axis are positive and heights below the principal axis are negative. So again, let us come back to the diagram, and from similarity you can always observe. If you consider the similarity of triangle OAB with triangle OA', B'. So these two triangles are already similar, and we realize that AB by A', B', this is A', this point is A', B' is equal to OA by OA'. Now, so this height of image to the height of object. If you see, AB is actually the height of the image, it is the height of the object, and A', B' is the height of the image. So if you apply sign convention here, what you get, AB is positive, so AB will be taken as positive. A', B', it is negative, so this will be taken as minus A', B' because this is height below the principal axis. What is OA? OA is the object distance, which is opposite to the incident ray. This is the incident ray and it is opposite, so this will be taken as minus U. And OA', it is the image distance, it will be taken positive because it is around the incident ray. So from here, if I apply the sign convention, I have to write the magnification is equal to height of image, which is negative, and height of object, which is positive, and that is equal to height of image for A', B' is V, and height of object, that is AB, that is U. This you can obviously reverse it. A', B' by AB is equal to V by U. So they are both negative. So ultimately what you get is the magnification which is equal to the height of the image, the height of the object is equal to V by U. Remember, even if we are applying sign convention during derivation, while solving numericals also we have to apply the same sign convention. So therefore the magnification of any lens will be equal to V by U. This will be the formula. So obviously for real objects, real images, the magnification will be negative, and for virtual images the magnification will be positive, because real images are always inverted and virtual images are always erect. So this is the conclusion regarding the magnification of a lens. It is also called as the linear magnification because we are comparing the heights. We could have compared the lengths also, and in that case also we would have got the same result. Whereas in the case of spherical mirrors, if you remember, the magnification was m equal to minus V by U. So we can summarize the formula that we have got in the case of the convex lens. It is equally applicable to a concave lens also. So let us summarize the formula that we have obtained. Let us summarize the formula that we have learned and the appropriate sign that we should consider whenever we are considering the object distance, the image distance, the focal length and the magnification. So object distance, as the object is generally placed in front of the lens, the object distance is negative for both convex as well as concave. This is negative. Now convex lens, in most of the cases it forms a real image, and for real image V is positive. So I am writing in this manner. This is positive for real image, and only one situation in which the object is between the focus and the optical center, then only the convex lens forms a real inverted and virtual erect and magnified image. So for virtual image, this is negative. So if the image is virtual, then V is negative. Whereas in the case of concave lens, it always forms a virtual image, and so V is always negative. V is always negative. Focal length of a convex lens, focal length means second principal focal length. The focal length is always positive for a convex lens. Focal length is negative for a concave lens. The magnification is negative for a real image. This is just opposite to V. It is negative for a real image because real images are always inverted, and it is positive for a virtual image. Whereas a concave lens always forms virtual image, so magnification is always positive for a concave lens. So this is how we can determine. Actually, there is no need to remember this, but I have summarized it. If you remember the proper sign convention, then these positive or negative symbols that we associate with U, V, F and M will be easily memorized, or easily you can realize that if you properly understand what is the sign convention. Every distance that is measured opposite to the direction of incident ray will be obviously negative, and every distance that we measure along the direction of the incident ray will be considered positive. Whenever you will study about the power of a lens, we will also see that the power of a convex lens is positive. Power of a convex lens, the power of any lens, the power of any lens, suppose P, let me call power as P, the power will be always 1 upon focal length. The power P of a lens will be always 1 upon focal length. So the power of a convex lens will be positive, and the power of a concave lens will be always negative. Because the focal length is positive for a convex lens, its power is also positive. Because F is positive, P is also positive. Because F is negative in concave lens, it is also negative, power is also negative in the case of a concave lens. And remember that power is just the reciprocal of the focal length. The power of a lens refers to the deviation that the lens will produce. Positive power means the lens is trying to converge the rays towards the principal axis, and negative power means the lens is trying to diverge the rays away from the principal axis, and that is why power for a convex lens is positive, whereas power for a concave lens is negative.